I want to go over dynamic programming because I know most people struggling in dynamic DP problems. And this is one of the common questions in most companies. Actually, in most interviews, you will have at least one DP problem, especially in on-site interviews. Usually, interviewers don't ask DP questions in the phone interviews. Before going inside of the DP, I want to share with you the steps if we have a DP problem. The first step is to solve using a brute force. Brute force approach. Brute force means we want to check all possible combinations. We want to search whole search space. In DP problems, actually, we have a search space in general, and we want to find some sub problems inside of that, and we want to call and test all of the search space combinations. Brute force, and we write actually recursive solution. Most of the time, recursive solution order is exponential. It is k power n. K can be 2, 3, or more. So this is the brute force, and most of the time, because it is recursive, the time complexity is exponential, so it is not acceptable solution, but it is good start. And I strongly recommend, if you have a DP problem, don't dive in the most optimum solution. Start with brute force approach and recursive solution, and discuss about the time complexity. Say, okay, this is exponential, and how we can, how we can decrease the time complexity. We know that in recursive calls, we solve lots of repetitive problems, repetitive sub problems. So in the second step, we use memoization to avoid all of the repetitive calculations. And usually we decrease the time complexity from exponential to a linear. Usually we have something like this, m times n, or n, it is not exponential. And in the memoization also, it's still in memoization solution, we have a still recursive solution, but we use a matrix to save the result of each sub problem. And whenever we reach to that, a same sub problem, we don't call our recursive calls. We use our already calculated answers. But after memoization, also we can improve our solution and convert the memoization to iterative solution. And we name this as a tabulation. We convert our memoization solution to tabulation. In the tabulation, actually, we have iterative solution. It is not recursive. And here, usually in tabulation, we decrease. It is possible to decrease space complexity. Usually we decrease space complexity, but sometimes if you are an embedded guy, even if tabulation, we don't decrease the space complexity because we don't use recursive calls. We don't use recursive solution. Definitely iterative solutions are preferred when you are coding in really resource limited embedded systems. So these are 3 steps, and I think the most important part is the first part, to be able to figure out and formulate the recursive formula. And I will teach you how you can mechanically convert the first solution to memoization and also memoization to tabulation. Also, people struggling, usually converting the memoization to tabulation. And I will show you how easy we will convert the memoization to tabulation without thinking about the problem. We will convert this, really, mechanically. Even we can, write a code for converting the memoization, right? We can write a script to convert any memoization algorithm to tabulation. We can automate it. But in most courses, most textbooks, in this phase, they make, again, they rephrase the problem and solve the problem from scratch for the tabulation parts. But you will see how I will help you to convert memoization without any effort to a tabulation. And usually when we talk about DP or DP algorithm, people's, purpose is the tabulation solution, the iterative solution. But if you want to dive in, directly in the iterative solution, it will be really tricky. And maybe when you see the DP or tabulation solution for DP problems, you will see how they made it. It is really, maybe you will think that, you need really, you need to be really creative to find that solution. But if you go from brute force approach, recursive and memoization and tabulation, you will see how easy you can make it. And this is the best approach for interview. But after you solve, let's say 10 problems, 5, 6, or to 10 problems, you can't directly write, even the tabulation, because you can see all this approach. You can see all of the steps in your mind, and you can directly dive in the recursive. So today I want to go one of the patterns, which is a DP pattern. We want to go over longest palindromic subsequence. So actually the name of pattern is longest palindromic subsequence. Why we say pattern? Because if you learn this pattern, you can map lots of problems to this pattern and solve them. Only the implementation may be a little different. So what is the question? Let's go and solve the first problem. So we are given a string. So we have a string. And we want to find, the objective is finding length of longest palindromic subsequence. Before I dive to the solution, I want to specify the difference between subsequence and substring. Or sometimes we say sublists. Let's say sublists. If we have let's say we have the string, and as an example, A, B, C, D, F, B, A. The substring is a continuous characters inside of the string. So for example, this is a ABC, D is a substring, or all of them should be connected. This is a substring, right? C, D, F, B. But subsequence, you can select any of characters, but they shouldn't be connected to each other. For example, A, C, D, A. I selected A, C, D, A, but the order should be, we shouldn't change the order. And we named this as a subsequence. And you should be aware of the difference of these two terms. Usually, you can, ask your, interviewer, but, you shouldn't waste your time for some really common terms. When we talk about subsequence, everyone knows, what's that. Okay, so let's say we have this string, and we want to find length of longest palindromic subsequence. And again, let me go to the palindromic. And when we say a string is palindromic, it means it is like this. You will say A, B, C, B, A. This is palindromic because it is symmetric. If you have, the symmetric line here, you will see that it is mirrors, right? Or if we have A, B, B, A, also, this is also palindrome. This is a palindrome, so it means that if you read, your string from the beginning to end, it will be equal to if you read your string from end to beginning. It means it is symmetric if you have the, if you split this into halves. So, but the question is, we want to find the longest palindromic subsequence. For example, for this string, I want to go and calculate this manually first, and then we will go in. So here, as you can see, AB and BA are palindrome. And I can add any of these guys, any of, C, D, or F, right? I can add one of these guys, and it will be my longest. So AB, let's say F, BA. This is longest palindromic subsequence. Okay, and we have to return 5 for this question. We have to return 5. Let me give you another example. A, B, B, C, B, B. We want to calculate, the longest palindromic subsequence here. As you can see, BB, BB, and C. So BB, C, BB. This is, again, our longest palindromic subsequence, 5. And let's say we have, all of them, A, B, C, D, E, F. We don't have any repetitive. And here, the longest palindromic subsequence is only any character, right? We cannot make even a string with length of 2. So the answer for this will be 1. Or let's say we have all of them same as each other, A. And the answer for this is 7. So I want to be sure everybody, right now knows, that what's the solution, what's the question. And let's go and think about this as a recursive solution, as a recursive approach. I want to write A, B, C, D. So I have A, B, C, D, F, B, A. And we want to find longest palindromic subsequence. When we have when we detect that I need to use a recursive approach to solve a problem, we need to focus on how I can divide my problem to 2 or more subproblems. Now the question is palindromic. We want to find a palindromic, and we know that the palindromic means, let's say the first element and the last element should be same as each other. Also, the second to the last should be exactly same as each other. right? As you can see, we need 2 pointers starting, from one of them starting from the beginning of our string and one of them from the end. First of all, we have to detect, how I wanna traverse my string. Most of the time when we have palindromic, any question regarding the palindromic strings, most of the time we need two pointers starting from beginning and the end, but we cannot, make it as a rule because, it depends on the question. So let's say I have here, one pointer here, I and J initially, right? How many options I have for the values of I and J? I mean, let's say this is my string and I is T of J. How many options we have for the values of these guys? Actually, in recursive problems, it is like probability problems we were solving in the high school or in the undergrad. You should think as you have a search space and you want to cover whole search space. Okay, so right now we have 2 values. How many options we have for these 2 guys? We have 2 options, right? They can be equal to each other or they cannot. They can be equal or they cannot be equal. And this will cover whole search space. Whenever I have a string, I have, for each step, I can find how many cases we have. This is the first step, how you can detect the subproblems. So I'm saying that right now, if we have, for the first, let's say the starting I is 0 and J is len of st minus 1. I'm checking at first if they are equal. So I hope I have palindromic subsequence inside of this, right? Because this is subsequence, if I call my function for this substring, for the remaining, right? If I call over this and calculate the length of the largest palindromic subsequence for this substring, assuming I have a function, and it returns the length of largest palindromic subsequence. You shouldn't dive inside of the recursive calls. So if I have this, they are equal, I will have, I can call my function, let's say my function, my recursive call, for the substring. I will call my function. I'm assuming the function returns length of the largest palindromic subsequence. And I will return 2 plus. I will return 2 plus function of this substring, right? But if they are not equal, let's say they are not equal. So if they are equal, definitely I will call function for the substring from I plus 1 and j minus 1. Let me write this here. We have A, B, C, D, F, B, A. We have 2 cases. J and I is here and J is here. If they are equal, I will return 2 plus and function with st, let's say from I plus 1 to j minus 1. You know, I'm writing this like in a pseudocode. Okay, because we know that if they are equal, definitely we have 2 for our length of our palindromic subsequence, and we know that this function, which is our recursive call, will return the length of the largest palindromic subsequence for that substring. But let's say they are not equal. If they are not equal, I have 2 options again. I can move I 1 unit forward, or I can move j 1 unit backward. It means that I will call the function st, our string, I plus 1 to j. I want to change. I know that, for my current I and j, I don't have any palindromic characters, right? I have 2 options: increase I and also increase, or increase j. Actually, decrease j. We have 2 options. So I will call my function for the substring. I know that this will return me the length of largest subsequence for this substring. The second call will return me, this call will return me the length of the largest palindromic substring for this substring. And I know I have, len 1, len 2. And I will return, because we want to find the maximum, right? Longest. I will return maximum of len 1 and len 2. So that's the case. This is the first part. We formulate the recursive formulas. And please don't dive in what's happening here. And let me a little. And our top call function is function st from, let's say, 0 to len minus 1. I'm not writing code right now. Len minus 1. Whole string, right? So when we call this function, we have 2 options in the top level, in the first level. First item and last item are equal. So I can call the same function for the substring inside of the substring by increasing I and decreasing j, and then plus 2. If they are not equal, definitely I don't have, I cannot count anything. I cannot increase my return value because they are not equal, and I have 2 options: increase I or decrease j. So based on this formulation, we can write our the code, and I will show you how we will populate, how we will write the base cases, which is really important. And this is, when you are writing the recursive solutions, most important part is base cases. But usually most people, try to write the base cases first. But for me, first I write the recursive formulas, and then based on those guys, I can detect, it's really easy, what should be my base cases. Let's go ahead and write the code based on the formulation that we made. I want to check, let me check, is there any question? No, and we don't. Okay, let's go. So let's go ahead and write the code for this problem. I want to define a function, actually, we'll say longest palindromic Actually, longest palindromic. I don't want to, let's say we want to repeat this subsequence. And we have a string as input. So if you remember, we said we need two indices, right? I and J, a start index and end index. Because we need more input arguments, input values, so we need a helper function. Actually, we cannot make the top level function recursive because we have only one input, which is a string. In order to formulate our recursive formulas, we need I and J. That's why we have to define another function, and we name this as a helper. So that's why I want to return. Let me write a little. Return helper st, and the initial I is 0, initial j is len of st minus 1. So this is our first call. Now it's time to define our recursive function. st, I want to make it really short, my code in the meetups. Usually we write start index, end index. In order to make it really short and compact the code, I use I and J. I know it is not professional for, when you are in your work. In real codes, you have to name really meaningful variables. But right now, in order to make it simple and short enough, I use, the shortest possible variables. So we know that in recursive solutions, first of all, we need to write the base cases, but I keep this to last step. I want to write first, as I said, I want to write first write, the recursive formulation, and then based on that, I can detect much more easier the base cases. So we said we have to check the first element, which is I and J, if they are equal to each other. We want to check the equality, right? If they are equal, we have to do something. So let's go and write the code. If sti is equal to stj, we will return 2 plus helper st I plus 1, because we want to go and call the inside the string inside of our whole string. I plus 1 and j minus 1. We will return this. Else, we don't need to write else because we have return here. Because we have return here, so we don't need to write else because it is automatically else, right? So, and then let's say this was my case 1 actually. We know that. And in case 2, they are not equal. I want to increase I and also decrease j. If you remember, I named len1 the previous slide. I want to call helper string. I want to increase I, but keep j. We don't want to change j. We want to skip only the first element. len2 is helper sti, but we want to decrease j. At the end, we want to return maximum of len1 and len2. Okay. So actually, when most of the time when we write the formula, the recursive part really correct, but our code is not working, That is because of the base cases. The base cases in recursive part is more the most critical part, and we shouldn't be really. I saw lots of my students, they struggle and they do some random changing the values of the base cases, the return values and the conditions we are checking. But you don't need to do really random things here. Everything is clear, and let's go and do what's happening here. Go see what's happening here. In order to check write the base cases without struggling, first of all, you have to check how many inputs we have in our recursive calls. So you have to check the inputs. A string, and you have to detect which one is variable, means we are changing. So as a string is fixed, so we don't need to check a string, right? But the I is variable, we are increasing, so I is increasing variable. Also J is decreasing. Because I is increasing, so we need to write upper bound for this guy. J is decreasing, we need to write lower bound. So our, the nature of, our, base cases will be, checking the upper bound for I and lower bound for J. When we check this, and then we will go back to the definition of our problem. So what is the definition? So I know that I have the string, let's say A, B, C, D, A, B, C, F, okay, something like this. I is here, J is here. I is increasing and J is decreasing. So we know that based on our definition, the problem, we don't want to, when they reach, when they meet each other, we don't want to go more, right? When they meet each other, we can return something. Let's say right now, I and J, for example, like this, I and J are pointing same character. So what does it mean? We want to say find the largest palindromic subsequence of a string starting from let's say 3 and ending at 3. It means that we have a substring with the length of 1, and the question is, what is the length of the largest palindromic substring of a character, 1 character? So what is the length of this? Definitely it is 1, right? So that's why we will write here, if I is equal to J, return 1. The returning will be based on the definition and the meaning of our function, our recursive call. I and J, it means we have a substring with the length of 1. And what is the length of largest or longest palindromic substring? Definitely it is 1. And sometimes it is possible to have I and J cross each other. Let's say we have AB. Starting I is here, J is here. The second step, J will point here, I will point here. It means I maybe will cross and will, pass J. So if we have this, what will be the answer? We'll say, I'm writing the condition, if I is greater than J. So we have a substring which is not valid. The substring from, let's say, the index of 2 to 1. We don't have any substring. So what is the length of the largest palindromic? For this substring, definitely we will return 0 because we don't have any substring. So even or we don't have any palindromic substring, so the length will be 0. This is the first solution. We talked about it, in the first of session, which is brute force. Why we say brute force? Because we check all combinations. We start one by one and we check all of the possible subsequences inside of our string, and based on that, we update our, the maximum length. But I want to go switch to the memoization parts. Why we need memoization? So before going to the memoization, let's calculate the time complexity of this algorithm. As you can see, the recursive part, the recursive solutions are really short, but the figuring out, formulating the formula maybe will be a little difficult. But if you don't dive in the recursive calls, I saw lots of people go in the recursive tree and see what's happening over there. It is really good to see this for 1 or 2 times and have a good feeling what's happening here. There is no magic. What's happening here, and we have a stack, and all of the values are stored in the stack, and then push and pop in the stack. You need to know this for 1 or 2 times, solve some problems and see and actually trace the code line by line in all the recursive calls. But after you do this, you did this for 1 or two times, don't do this for the other problems. Only see this as a some problems. You don't need to dive in the recursive calls, and it will guarantee to miss the interview. You should assume that the helper, for example, in this code, helper will return me a length. I don't know how it will return. I know that this helper will return the maximum length of the palindromic subsequence, starting from I+1 and j. And that's it. The magic has happened in base cases. And for base cases also, again, you don't need to do all the recursive tree. You should detect which variables are increasing, which one is decreasing. Sometimes variables we increase also have, and we decrease. We have to check upper bound and lower bound, both of them. And then based on the definition of the problem, you will detect what you should return, and you will detect what should be the conditions. But here, let's go to the time complexity. We start with I and j, which is 0 and let's say I'm writing n-1 or n-1. N is the length. At each step, one case is to go to this line, right? And we will have 1 and n-2. In another case, we have 2 recursive calls. We have 2 recursive calls, which is 0, actually no, 0, not 0, 1 and n-1. And also, I'm writing only the variables. When you write the recursive call, I'm doing this for once, and you don't need to write your whole recursive tree, even if you wanna find your time complexity. But I wanna do this once, and then you won't need this guy. So we call this, or we will call 0 and n-2. And again, for each of these guys, we will have, as you can see, we have 2 options. We can have only 1 recursive call, or at each call, we can have 2 recursive calls. It means that in the base case, that's, we have A, B, C, B, A, let's say, the palindromic string. We will go only, this line, right? And our tree will be a chain. We will have something like this. We will call recursive calls linear, but this is the best case. And we want to find the worst case. Worst case is they are not equal at all. It means that at each step, we call 2 recursive calls. And again, for each of these guys, we have 2 recursive calls. So we have this or this. But the worst case is this guy, you know, I mean, in whole cases, we call these two recursive calls. We call these two guys. Because at each recursive call, we call it to another one, we say the time complexity is order of 2 power n. 2 power n, n is length of substring, length of the string. Actually here, because we only traverse the half of the string, it is 2 power n divided by 2. It is not n actually. But again, because this is constant, we don't say it is 2 power n divided by 2. We say 2 power n because this is a constant. If we have 3 recursive calls, we will say 3 power n. And that's, you know, how we calculate the time complexity of the recursive solutions. What's the reason? Because, you know, here, let's say we have 3 characters, right? You know, we have here, let's say we have, let me raise this. I want to, actually, the recursive, the time complexity is whole nodes of this binary tree. And the order of this is 2 power n. This is 2 power n order, right? And so time complexity is 2 power n because we, at each step, we call 2 recursive calls. And let's go and calculate the space complexity. The space, you have to calculate the number of levels, how many levels we have. Because at each level, we store some values in the stack. And actually we are talking about the space is related to stack space for our recursive calls. And here, if we have a string with the length of n, we have n levels, right? So we will have n space, actually it is n divided by 2. But again, order of n divided by 2 is equivalent to, in terms of O, we can write order of n. So that's it, you know, whenever, you know, you detect that, how many branches you have in your, you know, recursive tree, immediately you can, you know, write your time complexity. And then based on the number of levels, usually it is log of your time complexity. Log of 2 power n is n. It will be your stack space because we don't use another, you know, data structure here. So the space complexity will be order of n. So, but 2 power n is not acceptable. This is really exponential time complexity is terrible. So we have to check, maybe we call some repetitive functions. Let's go and check for a simple example, a basic example, and see we are calling some repetitive functions. We are solving problem for some subsequence, for some substrings for several times. Let's say the variables are started from 0 and let's say 5. I'm assuming I have a string A, B, C, B, let's say B. So the start index will be 0, 1, 2, 3, 4. So let's say I make it 4. So we have for this guy, if we go to the case 1, we will call 1 and 3. If we go to the case 2, we will have 2 calls. And it is 1 and 4 and 0 and 3. Okay. And the next time, if we have 1 and 3, again, we will have 1 for case 1 and the 2 cases, you know, for 2 recursive calls for case 2. If you have the case 1, we will have 2 and 2, and it's done because we, actually it is the base case. We don't have more recursive calls. Or if you have in case 2, when I'm saying in the case 2, I mean it is here. Let me write the names here. Here is case 1, and here is case 2. Okay, so in case 2, for 1 and 3, we will have 2 and 3. We will call the recursive function with these variable inputs. Or we will have 1 and 2. And again, we will go for this guy. Because it is happening when we run this code for recursive calls. 1 and 4, we will have 2 and 3 for the case 1. We have 2 and 4. We have 1 and 3. As you can see, we already calculated 1 and 3. We called a function with 1 and 3. I don't need to call this again. I have to use the value of my function, the return value of the function when I'm calling with 1 and 3, and use it. I don't need to call it again. Or for example, for 2 and 3, we already calculated here 2 and 3. I don't need to recall. I have to use my value here. That's why we wanna avoid all of these repetitive recursive calls using the memoization technique. Memoization means we want to use a memory to keep all the values, and whenever we want to calculate, before calculating or calling our recursive calls, we will check if we already calculated this solve problem. We should only return it. So let's go and convert this code to memoization version. You will see how easy is this part also. Let me erase these parts to have a little more clean. Okay, we need a memo, or sometimes we say DP matrix. I want to know what will be the size of my matrix. First of all, we have to detect what is the dimension of my matrix. So in order to figure out, you have to check how many variables you have. We have 2 variables, I and j. What is the range for I in the worst case? I is going from 0 to 0 to n-1. Also, j is going from 0 to n-1, right? The range, the valid range for 0 and for I and j is the length of the our string. So I need a matrix because I want to calculate all of the I and j's, all of the possible values of I and j's, and put them in a memory. So I need a matrix I and j. Let's say our string, the length is, let's say A, B, C, B, F. Is 0, 1, 2, 3, 4. So let's say, so we'll have 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So I want to create a matrix with this dimension. We want to create this. Whenever we calculate, we want to update the value, and then we will use it. So let's go and do this here. I want to use another color for this part, the red color. So I want to create a matrix, a two-dimensional matrix. If actually this is different in different languages. I usually use memo for memoization, and I want to define with the -1 as initial value, because we know that the -1 doesn't mean, it is not a valid return value for the length of a substring, right, or subsequence. -1 for, let's say, X, or we can write it the underscore. Usually I want to make this a little readable here, but I know that it is a little, if you are not a Python guy, it will be a little difficult for you, but you can the objective is this is our memo. The objective is to define this matrix. So when I'm defining the first parts, this guy, this is a matrix with the a list, actually, a list with the length of len of the string, which is one of these guys. And I want to repeat this for 5 times. So that's why I'm writing here, and then 4, again, X or anything, let's say randomly Y in range len of string. And at the end, we'll have brackets. The first thing we need to do is to figure out what is the size of my memo matrix and define it. And we have to pass this to our recursive call, because we want to keep it in all of our recursive calls. So let me raise this guy, and we have to add memo as inputs. So we need to add memo also here. Okay, so we have memo. Before calling all of recursive calls, we have to check if we already calculated this guy or not. I don't have a space here. Maybe I can move this a little up. To have a space here, because I want to add the code exactly here. So before, in a base cases, you should check base cases at first. We don't need to change, do this, before the base case, but even, it is better to do this after base cases. So here you will write, if for I and j, we already calculated. We will say if memo of I and j is not equal to -1. It means that we already set the value, and we already calculated this. You say if it is not equal to -1, return it, and don't call all the recursive calls, because we have answer for this subproblem. What is the subproblem? Subproblem is a helper with starting from A and ending in the J. And at the end, when whenever we return a value, we have to update. We are returning here, and also we are returning here, right? In 2 places we are returning, or actually we are calculating a value for I and j. We have to update our, the memo. So that's why we have to update our memo here. So actually it will be memo I and j. Let me make it a little. Will be equal to 2+. Because right now we calculate this, and we have to update our memo. And then we will return memo I and j. We didn't do any special thing here, right? Instead of returning 2 plus helper, we save this in the memo and then we return it. And also at the end, we have to first update memo. Before any return, you have to update your memo. I and j is equal to max of len 1, len 2. Actually, we can keep this max, but I think it is not a good idea because we don't want to calculate max twice. It will work, but it is better to, because we put this in I, memo I and j, it is better to return this. As you can see, the red parts are exactly the updates to make our the second step. The second step we talked about it was the memoization. The idea is whenever I'm calculating the problem for a sub, I'm calculating one of the sub problems, I want to save the results. And next time, it's I want to calculate this, I don't want to call all the recursive calls. So what will be the time complexity for this question? Let me check. Do we have any? Any question or? Let me check here. Okay, we don't have any question. Okay, let's go. So now we're gonna check our time complexity. We know that the whole search space is this matrix. We definitely we won't call more. We don't calculate the problems more than this number of cells here, right? Because if we already have the value, we will return it. So it means that the time complexity will be order of n squared. So we decrease this guy to order of n squared. Because we know that this is n and this is n. And the space complexity right now, we know that stack space is still n, but we are using this matrix. And because this is, yes, okay, there's a comment, thank you. Yeah, I forgot to, I forgot, in two cases. In recursive calls, you have to add memo. Usually we forgot this, in the, it's really easy to miss this part. Memo, memo, and memo. We have to pass memo in all, our recursive calls. And also, in base cases, also you need to update your memo. But actually, in base cases, we don't need, because the question was, to add the memo in the base cases. But actually, we don't need that one because we return it. We don't need to add this in the, the update our memo matrix. But these parts are really important. This part and this part, because if you don't have, you will have a syntax error. But for returning in the base cases, you don't need, because we are returning the value. We don't go and call all our recursive calls. So I was talking about the space complexity. The space complexity, we said n is exactly again our the stack space because of our recursive calls, but we have order of n squared for our memoization, which is greater, so our time space complexity will be n squared. But this is definitely better because we decreased exponential to polynomial. right? And or n squared, and definitely we have to do this. So any question? If let me wait a little to see if anyone has any question. Okay, let me go. Let's go to the last part, converting the memoization to tabulation, which is really tricky. In most textbooks and courses I saw, even in the grokking, I really love this, but the tabulation part is a little, they made it a little complicated. We don't need to rephrase the problem to convert the memoization to tabulation. You can automatically and mechanically convert this. So actually, the objective is converting this memoization algorithm to an iterative. We don't want to have recursive calls, and we will handle this by populating a matrix. And we already have this matrix, right? We want to use exactly this matrix. Instead of calling the recursive calls to fill all the values, we want to fill all the values manually using the iterative solution. So what is the first step? I want to have this. Okay. So the first step is define our DP matrix. I'm using memo matrix for memoization and DP matrix for tabulation. So we want to define our DP. So again, based on I and J, usually you can work based on your memo matrix. Sometimes we need to add some rows or columns, but your initial point is use the memo matrix, okay? And we already have it. So let me write here. The first step, step 1, start with memo matrix as DP matrix. Okay, so we want to start with this. Step 2 is check base cases. So we want to check the base cases and update DP matrix. So for example here, what is the base case? We say if I and j is equal, return 1. What does it mean? I and j is equal is this cell, this, and this, right? Return 1, so we will put 1 here. I'm writing 1 here. 1, 1, 1, 1. Okay, so this is the 1. If I is greater than j, return 0. So, and we know that, let me make it a little, and this is my, it's not memo, this is DP. And I don't need these guys. Let me make it a little clean here. Okay, so I is greater than j is 0. So we know that this part, this triangle, always I is greater than j, right? I is greater than j, all of them. So, and we will return 0. So based on base cases, we populate our matrix. So, so far we didn't do anything. We didn't rethink about the problem. Only we converted our memo to DP, and based on the base cases, we updated our cells. I don't want to change the problem definition. Most of the time, people change, the direction of the approach. in memoization when they change it. For example, we can start the string from start to the end. They change this to starting from end to the beginning, and you need to again focus on the meaning of the problem. And in tabulation part, you need to resolve the solution. But right now with this method, you don't need to resolve. You're only converting. So step 3. Write recursive formulas. So how we will write the recursive formulas? I hope I want to do all of these in this whiteboard. I don't want to create another whiteboard for this part. Okay. So based on exactly again all of our say based on these equations, you have to check where you have your recursive calls. Whenever we have a recursive call like this or this, we will write DP. So when I'm calling, let's say I'm calling this call, it means DP of I want to convert this to the equation. How should I convert this? Let me make this blue color. So how can I convert this to the equation, DP equation? I will write DP I and J. We know that the variables are I and J, and the input is I and J. And whenever we again call our function, we have one case here. We have one case here, one case here, and one case here. For each of these guys, we have to write a formula, right? So we will write DP I and J is equal to, for example, for this case, the first case 1 is equal to 2 plus, and again, we have recursive call, you have to write DP of I plus 1, J minus 1, without changing anything. But we will have one if statement here. I don't want to write, right now, if STI is equal to STJ, DP will be this, right? Else, we will have DP of I and J will be equal to maximum of this guy and this guy. So how can I convert this guy? A DP will be DP of I plus 1 and J. So I will write it is maximum of DP of I plus 1 and J, comma, DP of I and J minus 1. And that's it. This is the most important part of your DP solution. It means that based on these base cases, how I want to populate these values. How? Based on these equations. How we wrote them? How we wrote these equations? Exactly, we converted our memoization solution to the tabulation. Let me make my substance silent. Okay. Okay. So right now, in order to see how we are, so this is the step 4, step 3, and what is the step 4? I want to write here step 4. We have to detect the direction of calculations, the direction of populating, direction of calculations, let's say I wanted to say, or maybe directional, let's say populating the matrix, populating the matrix. I mean, if I want to calculate, I should start from here and then go here. How can I calculate these guys based on these equations? For this part, again, we have to focus on our equations, and we have here. We see that in order to find I and j, let's say I'm here. This is my I and j. In random, I'm selecting like this guy, I and j, which is 1 and 3. I need, let's say I have 1 and 3. I need 2 and 2, right? 1 and 3, I need 2 and 2 to calculate. Also, I need 2 and 3. I need 1 and 2. So it means that in order to calculate this cell, I need 1 and 2, which is this cell, 2 and 3, which is this cell, 2 and 2, which is this cell. It means that for each node, I need all these neighbors to calculate it. Left neighbor, bottom neighbor, and the bottom left. Based on this, we will detect how we can populate our, the matrix. Because we want to populate our matrix and, populate all the values, all the cell values. So it means that I can calculate this definitely because I have all the values of the neighbors based on that, the formulas. If I calculate this, can I calculate this guy? No, right? We cannot calculate this guy. And so it means that I can calculate, after this, it's better to calculate this guy. So we will calculate this one because we have all the values to be able to calculate this. And then we will calculate this. If you have these two, I can calculate this. I can calculate here because I have the neighbors. If I have this, I can calculate this, and then this. So it means that we detected based on equations, I need to do something like this to calculate all of them. And usually, but you have to be careful about the problem definition. Usually the last element is your answer. Last element is your answer, but I will solve, even the next sessions, more DP problems in this way, and you will see how we will detect which one is the answer. So right now we can calculate, this cell easily, right? So we are here, string 3. It depends on, what is my string. Let's say, I want to go only with some steps. Let's say A, B, C, D, A. Okay, we have this, right? So right now we want to go and I3, J4. It means D and A. They are equal or not? They are not equal, so I need to calculate this based on this and this. I don't need, this cell. Because if they are equal, we are using this equation. If they are not equal, we have to find the maximum of these guys. So after you understand, how you are calculating, it's a 1 and 1. What is the maximum of 1 and 1 is 1. Oh, 1. And I want to go here. 3 and 2. 0, 1, 2, 3, 4, right? 2 and 3 are not equal. So the maximum 1 and 1 is 1. I'm here. 2 and 4, they are not equal. They are not equal. So maximum of 1 and 1 will be again 1. Right? 1 and 2. 1 and 2, they are not equal because it is, so maximum of 1 and 1 will be 1. 1 and 3, they are not equal because it is B. 1 is index 1 is B, index 3 is D. So again, 1 we will have here. 1 and 4, which is index 1 is B, index 4 is A. They are not equal, so maximum will be 1. 0 and 1, same, because A and B are not equal. Maybe I should have better example. And 0 and 2, they are not equal. It will be 1. 0 and 3, they are not equal. Again, maximum of this and this will be 1. 0 and 4 are equal. So it will be the value of the cell plus 2 based on this equation, because they are will be 3. And 3 is our output. And we will return 3. Okay. Well, this is the way I could have, better, example, let's say if you have palindromic, you will see how, as you can see, we detected how we have to populate the matrix based on the equations, actually. So I want to start, right now, everything is ready to write the code of the DP parts. We have these guys, we have the equations. We know how to populate the matrix. It is ready to write the code for the DP parts. I don't know, can I copy this to the next whiteboard or not? I didn't do this before. There is no copy. Okay, there is no copy. I have to write them again. Okay, doesn't matter. Let's go to the next one. And I wanna background should be okay. So let's go and write whole code here for the so we will write again, define the, let's say, length of longest palindromic. So I want to write, the naming is not here in tabulation. The tabulation solution. So we have a string. So before, because we need to know the length of the string, it is better to, first of all, calculate the length of the string, which is n. And do you remember we said we need a DP array of matrix. We created this, for in memoization. This is exactly the same. I am putting in a 0 as initial value because we will update. Let me back to the previous one. We know that these parts actually are 0. And actually the diagonal is 1, and we will update all the other parts. So the initial value 0 is really reasonable. We will put 0 and we will override all of these ones, and then we will populate all of these values. So that's why I want to do the 0 for, let's say in Python, we don't need to even, underscore is enough, range n. So this is the first row, and I want to repeat this for n times to make my matrix. Okay, this is my DP. So the next step is to do the, do you remember, I want to again switch here. I want to populate this row, the base case. Actually, with initialization to 0, we did all automatically this part. Now I want to populate the ones here in my DP. So I need a for loop. I need a for loop. I will write for I in range n dp I and I, because we want to make one whole, the diagonal, right? So we made it, and now we want to go and populate all of these cells. I need 2 for loops, right? Because I need one for loop to, control my row, and another for loop for controlling my column. And the starting row is n-2, right? I will start with the last part. Actually, we can also, we have 2 options here. We can start from here. Also, we can start from here, but let's go from here, right? And so our I will go from 3 to 0, and J will go from, if it is 3, J will start from 4. If it is I is 2, J will start from 3 over n. If I is 1, J will start from 2, which is I plus 1, until the end of the array. If I is 0, we will start from I plus 1, which is 1 over the end. So we know our for loops. So I want to go write my, the populating part for J. I want to go J from, the first one actually is here. Let me check my. Okay. So we want to start from here. I will be n-1, n-2 actually. Let's start with the I. So we'll write for I in range. So what is the first value for I? We will start from n-2, right? Because n-1 is 4, which is last row. We have it. n-2. So we will start with n-2. And we want to go over, I will go n-1 to 0. So you will write -1 and -1. So -1 is end, and this is the opposite direction. Okay. So we will have this, and let's go and write J. J will go I plus 1. We will go I plus 1 over until the end of the array. End of the array is n. And we know that the reason I'm writing here -1, because in Python, these ranges are not inclusive. You have to write -1. It means that it will go over 3, over the 0. And when you write n, it means it will go over until the n-1. So based on the directions, you will you will detect how you should write your for loops. And then you will write your formulas, and we have this, we did this, before. If st of I is equal to st string of j, you will write dp of I and j is equal to 2 plus dp of I plus 1 j minus 1. Else dp of, actually we did this in the blue with blue color in the previous whiteboard, right? Maximum of dp of I plus 1 in J and dp of, let me, I and J minus 1. So we will do this. At the end, as we said, we want to return the last element of the first row, which will be dp of first row and the last element, which is n minus 1. Actually, this is, how we converted our memoization algorithm to tabulation. As you see, we didn't do any rethinking about it. I think the only part you have to think about it is finding the direction of your populating, how you want to calculate it. That's it. And it is not really a difficult thing based on the formulas you developed, based on the recursive calls. We based on the recursive calls here, here, and here, we created our recursive, our DP formulations. And based on the base cases, we populated the initial values. Again, based on these formulas, you can detect how should I the populates, right? And actually, we could populate even in this way. We'll say someone maybe will say, I want to calculate first this and this and this and this, and then we can do different ways. We can calculate these rows because for each row we have all the requirements, and then calculate these guys and this and this. You can populate in this way. I did in this way. We don't have one solution for the populating, but the populating part only will change your for loops, these parts. And this part and also the initialization will be done automatically and directly based on the base cases. And based on the formulas, you will detect the populating parts. So let's go and calculate the time complexity and space complexity for this solution. So again, as you can see, we populate whole matrix, right? Actually, we don't populate whole matrix because we do n times, here, this is order of n. And this part, actually, we do the order of n squared divided by 2. But in terms of when we write big O, it is equivalent to order of n squared. So the time complexity is order of n squared, and space is equal to order of n squared because we used this matrix, right? The DP matrix is n squared. So there is a question. Let me check this. Is this the expected workflow to follow in an interview? Recursive solution, then optimize, or would skipping straight to an optimal solution be better if possible? Would this reflect a good or typical problem-solving technique during on the? So if you have a DP problem, if you go based on the recursive, and then convert into memoization and then DP, it shows that you can think systematically. You can see, you can handle a problem step by step. It is really, helpful. I did, in my interviews, all my interviews, I had, in all of them DP problems, and for all of them I did these steps. And when interviewers, sees that you are really, going step by step without struggling, definitely you will get the offer. Definitely you will get the offer. I think that would be, I strongly recommend go over recursive memoization. Actually, you know that the recursive, in converting you can write directly the memoization. If you solve some problems, you can write directly the memoization. But if in the interviewers, prefer to see this how you are thinking, and definitely in this way, the risk will be really low, and you will show how you are relaxed during the interview, and you are not struggling. I'm emphasizing on struggling, even if you develop the optimal solution, but you struggle a lot to find the optimal solution. I compare two people, two interviewees. One of them, giving you the optimal solution, but with lots of struggling, and another one, gives you maybe suboptimal even, we'll say, but he or she is really relaxed with high self-confidence, control on his or her emotions. Definitely, interviewer will give higher grade for the second one, not the first one. That's why I strongly recommend go based on step-by-step solutions. But again, if you can't directly write a memo and then converting the memo to the tabulation, you need a little think about it. But in the courses, in grokking and cracking the coding interview, textbook, and all whole textbooks I saw in the internet, in the market, I saw they changed the the definition of the problem when they want to write the tabulation parts. Say, okay, what is the meaning? They focus on the meaning of each cell. It is good, and you can change, and the populating will be much more, that the populating part will be starting from 0 to n, right? But in that way, you need to rethink and rephrase the problem and map the problem again in the matrix. But with the method, actually I'm using, it works for, more than 90% of the DP problems. Some of them, you need to again rephrase the problem, but it works for more than 90% of the problems. Directly convert the memoization to tabulation, and you will see even the next session, because the DP I saw a lot. DP is one of the areas most people are struggling about it. That's why in meetups I spend more time on the DP, the weak part of the most people. So we said this is order of n squared, and the space is order of n squared. So can we optimize the space complexity? Do we need a matrix necessary? Do we need whole matrix to calculate our values here? So as you can see, for each element, we need one item from this next row and another one from the current row, right? Actually, we can write this code with only 2 rows, but because each row is changing, when we go row by row, as you can see, the values of rows are changing. It is possible, you can discuss in the interview, that I can decrease, let's say, if I have only these first 2 rows, and then I can calculate the 3rd row updates in here, and again 4th row here. But this problem is a little difficult to convert this to writing the tabulation with only 2 rows. It means converting this guy to, do you have any question? I think one of the guys, sorry. Let me check here. We have a little noise here. Okay. Sorry, you know, I needed to mute, you know, one of the guys. Okay, so the space we can decrease to order of n, but this case is a little complicated. We have lots of, you know, we will see in the next sessions that's, you know, we can easily convert this matrix only to 2 rows, a matrix with only 2 rows, and we will decrease the space complexity to order of n. But here, because, you know, row is, you know, changing, it will be a little, you know, it's not really efficient. And in most interviews, when you do the recursive part and memoization, usually they say, okay, you don't need to do the tabulation. Only, you know, in some of my interviews, because there is no time, there isn't no time to, there isn't enough time actually to do all of these parts. And the interviewer, when the interviewer sees that, you know, you are, you know, doing perfect in populating, in the formulating the formulas, they say, okay, what's the next step? You say, okay, I can do the tabulation. And then I can, maybe I can decrease the space complexity from n squared to n, right? And we will have a little simpler examples in the next session, and you will see how we can convert this to a little more optimal solution in terms of a space complexity. But here I don't want to go that, you know, because it is, this problem is not the case that's, you know, we want to do that. Okay. So I think, you know, that the DP problems, I intentionally, you know, go really slow because I don't know the level of all of the attendees. I do my best to satisfy, you know, most people. I know some people know, maybe know these problems already. That's why, but I'm trying to be really slow and teach, you know, all of the steps step by step. Because if you learn one problem really perfect, it is much more better than to solve 10 problems. But, you know, you don't know what's going on. So, you know, you actually memorizing the problem. It's all, I saw lots of people, they memorize the, you know, the solutions. We don't need to memorize. We need to learn, you know, if we learn one problem really perfect, we can map the problem to lots of other problems. So in the next step, I want to go and I want to write the first, you know, the recursive solution and maybe the memoization if we have time. I want to go over, you know, until, you know, 8:15 because, you know, we had, you know, 15 minutes. We started really 15 minutes late. And then please go and write a DP problem yourself. Convert the memoization to DP. And the next session, if you have any question, in the next session, definitely I will answer your questions. Okay, there is a comment. They are clearly understand. Yeah, perfect. Thanks for the comments. Okay, let's go and to the next pattern. The first pattern, when we say the pattern, because you have to be careful when you are learning, you know, the pattern, right? You have to be careful in the next problems. If you see you have palindromic subsequences, you have to you know, in your mind should be triggered this pattern. In most cases, if you have, you know, the palindromic subsequence, you have to be you have to think about this, you know, solution, you know, how we made it. We had, you know, 2 indices from start and end, and we started in recursive calls, right? And whenever you see palindromic, you know, questions for strings, and you want to find the subsequence, any calculations, most of the time you will need to use this pattern. And if you are fluent in this implementation of this code, that will be really super easy for you guys. The next problem is same, but instead of subsequence, we want to say substring. So we want to find length of here, length of largest palindromic substring. So we want to do this. Let me, because, you know, this is so similar to the previous problem, but, you know, you need to know how to formulate this problem. So let me give you some examples. Let's say we have A, B, D, let's say B, C, A. You want to find palindromic substring. Substring means they should be continuous, right? So here we see that BDB is the longest, right? And so we will return 3. Or let's say we have A, B, C, B, C, D, C, B, A. So here, A, so you can see that, you know, we have B, C, D. This is the longest palindromic substring. I hope, you know, we don't have larger than this. I think B, C, D, C, B, yeah. We have 5. So this is the question. The difference is we don't want to have subsequence. We have more limitation, right? You know, subsequence is more general, you know, compared to the substring. Substring is a subset of, you know, subsequence, right? Any substring is a subsequence, but, you know, any subsequence is not a substring. So we have more limitation. We have previous problem, more limitation, but we want to use same pattern. We don't want to use another pattern. Okay. So let's go with the first example and solve this manually first, and then we will go and write the code. If you know, in the interviews, don't worry about the developing or implementing your idea. If you figure out the, you know, what's the algorithm, which pattern you want to use, implementation will be only in 5 minutes. If you know, already solved, you know, for each pattern at least 10 problems, you know, not 10 problems, even 5 problems for each pattern will give you enough self-confidence to solve or develop any, you know, any new problem, the solution for any new problem in 5 minutes. So if you have 20 minutes, most of, you know, interviews, we have only 20 minutes to solve a solution. I'm talking about the on-site interviews. In phone interview, you have more time. 20 minutes, even if you are, you know, I mean, some people say, you know, I wasted my time, you know, for 15 minutes to talking about the algorithm. If you find the algorithm, exactly what you want to do in first 15 minutes, in the last 5 minutes, you can write, you know, easily the algorithm. So first of all, you have to understand how you want to solve it. So here, again, I want to start with I and J. Because it is palindromic, it seems that, you know, this pattern will help us. So here again, if they are equal, can I say 2 plus, you know, helper? You know, let's say the helper, you know, I mean, you know, the largest is helper of, you know, the function. Because right now, you know, we have 2 plus, I'm not sure, you know, the length of this. If the length of this exactly 4 for this example, it means that whole substring is palindromic, right? And then I can return 2 plus this guy. But if it is not, it means that, you know, I cannot use these guys, right? There is no I have to go inside, right? If they are equal, and the return value of the substring, the shrink substring, if it is exactly 4, I will return 2 plus 4, which is 5, which is 6. If it is not, we will have same scenario we had before. So because of the limitation, we need one more condition here. The previous one we said you can write in a 2 plus helper for the substring, right? The internal substring. But right now we cannot say 2 plus this. We will say if the length of the the helper, actually the return value of this guy is equal to 4, or my remaining length, I have to return it. If not, so I shouldn't return anything, and I will go and increase I once and decrease J. So that's why we have exactly same code with only one more condition. It seems at first it is really, complicated, but it's not. And this is the power of the learning the patterns. If you learn once, and you can, find, you can, solve lots of other problems. So let's go and write the code. I wanna write the code, and you will see how, actually I can return to the our previous solution, but I prefer to write from scratch here. It doesn't take a lot of time. So we want to write define length of let's say largest or longest. I don't know why I'm writing largest. There's a longest. Longest palindromic substring. So we have a string st as input. So again, we need to a helper st 0 and len of st minus 1. Let's go and define our helper. Helper is, or recursive function actually, will be a string I and j. Again, because we know the base cases are exactly same, I don't want to write at the end, because we already did this. I is greater than j, we will return 0, and we said if I is equal to j, we return 1, because we have a string with only one character. So the length is this, and then we will check if st a string of I is equal to a string of j. I don't want to return it. I have to calculate this. So I will write. Len 1. I want to write len 1 is equal to helper. If they are equal, write st string I plus 1 and j minus 1. Okay. I plus 1 and j minus 1. But I have to check if len 1 is equal to, so if I have I and j, what will be the length of this guy? Let's say I right now is 0, j is 0, 1, 2, 3, 4, 5, right? So will be j minus I will be 5, right? Minus 1. I saw, lots of people, struggling in calculation with only a simple example, a basic example you can figure out, the formulas, right? I is 0, j is 5. I need to have 4, so I have to have 5 minus 0 minus 1. If len 1 is equal to j minus I minus 1, yes, I have, I have to return. I have to return 2 plus len 1, right? So this is the exactly we said, this is case 1. The case 2 is they are not equal, exactly same as previous problem. We have to skip the first character or skip the last character. So we will have len, let's say, I want to write 2. Actually, 1 is internal. I can't use the len 1, but I want to make it a little readable. Helper will be st I plus 1. I don't want to change j. Len 3 will be helper st. I don't want to change I, but I want to decrease j. At the end, I will return maximum of len 2 and len 3. So as you can see, we have only one more if statement here, and it's done. Only because of the more. So this is the way I'm thinking when I'm doing the patterns. When I know a similar problem I solved before, say, okay, this is my base, and do we have more assumptions, or it is, in most cases, if you detect the problem has a special case of your problem, definitely you can use the pattern, right? But sometimes you know something, but the question is more general than your question, which is limited. In those cases, sometimes the pattern, you have to find some other pattern. Maybe this pattern is not the case. But if you detect that it is same question, but you have more assumptions, more limitations, or less limitation, it will help you to use the patterns you already learned. Okay, so now we have this, but the important part is here is time complexity. I don't want to talk about the solution again, because I think everything is clear. I hope it is clear. And let's go and calculate the time complexity. Time and space. So do you remember I said you have to check the number of recursive calls? In the previous one, we said in worst case, we had 2 recursive calls, right? Because sometimes we will returning from this if statement, and sometimes we will hire. So, but in case 1, in the previous, I'm talking about the previous problem, the subsequence, the worst case was here, and we had 2s. That's why we said 2 power n. But here in this problem, actually we are calling this guy, and we don't return. It is possible to call this function call, this recursive call, but don't return. I mean, in worst case, you have 1, 2, 1, 2, and 3 recursive calls. You have to think about only the worst case if you want to do the big O. Don't dive in again, all the recursive calls. Okay. I'm calling in the worst cases. I'm calling, because if is this, I will call this, but maybe the len is not equal to j minus 1, and then again I will call this. And in the worst case, at each call I will call 3 recursive calls. So that's why I will say order is 3 power n. And again, the number of levels in our tree will be order of n. Most of the time you have to take the log of this guy. Log of this will be, n again. The order is n. But you should say, take the log in base of 3. That doesn't matter. The base is not important. And this and this. And the memoization, it is really clear. There is nothing new here compared to the previous problem in memoization. And but in the tabulation, you have a little difference. You need to check one more. But again, it won't be changed. Only your formulas will be changed, right? Only the let me do tabulation. Only this part will be changed. This part. For this part, you will have one more if statements for the tabulation part. Please do this, the tabulation part. And if you like the memoization for the next session,